Hi, thank you to everyone who came back from lunch in time. So we are starting now with our penultimate session for today about an emerging technology which might be affecting all of our work and all of our lives if it takes up. So we have a special guest today to discuss about the technology. He's coming straight from Denmark, his first time in Belgrade. So please let's welcome STIG.
Thanks for having me.
STIG, thank you and welcome to Belgrade. I understand this is your Xth time in Belgrade?
My first time in Belgrade.
Oh, your first time in Belgrade. Oh my goodness. Okay. Well, I hope it's been treating you nice, you know, with all the rain and all the road works, and you know, you managed to come here, so it's already a success, right?
Yeah.
Good, good, good. What will you be talking to us? What will you be talking about today?
I'll be talking about quantum computers and how to use them for real problems, and whether it will be relevant for some of you if you're in the right business, and well, it will be relevant for you.
Good. Any other technology that we should be aware of, similar to quantum computers, that is emerging and might be coming, or sort of is on the tipping point? Where do we invest?
Well,
we are late for SpaceX, obviously.
I would say, yeah. Besides SpaceX, you should definitely invest in quantum computers around now, because
quantum, right?
Yeah, it is an emerging technology, and it will blow up within the next 5 to 10 years. It will be relevant to many industries. Some industries with a lot of money in it, so it will be important.
Okay. Is it somewhere in terms of development and emergence, is it somewhere on the level of hydrogen as fuel, or?
Yeah. I mean, hydrogen as fuel is something that is a bit more on the hardware side. It's not something that you, as a software developer, would need to know that much about. But quantum computers, you need to know something about if you're developing software, because it will, at some point, be a part of your software if you're building software that needs to calculate a lot of things.
Amazing, thank you. Anything that we should know about you? I understand you've been skiing a lot.
Yeah. I ski a lot, and mostly in the Alps and around the world. Been to Japan and Canada to ski. I have not skied in Serbia, but I've heard you had a few small resorts here.
Probably skiers will suggest you stick to the Alps.
All right, I'll stay in the Alps then.
How is skiing in Japan? Should we plan to go to Kyoto or wherever?
Yeah, it's really wonderful. There are a lot of mountains, and they have plenty of snow. Really much beautiful snow to ski in. So it's very wonderful.
If you were thinking where to go in the next few months, Japan ski holiday sounds very doable. Good. STIG, I leave you with our audience.
Thank you.
Audience, I leave STIG with you. He's new to Belgrade. Please take good care of him. There will be a Q&A session, so make sure you leave the 10-ish or so minutes for the end.
For questions, yeah.
The timer is here. The questions will come up there. Audience, please do not spare STIG. He's young. He's very enthusiastic.
Indeed.
He decided to focus on quantum computing based on?
Yeah, when I was a kid, I actually saw a lot of science fiction movies about everything, and then at some point there was this quantum computer that was like this weird thing in the science fiction movies. And I actually told my teacher in the elementary school that when I grow up I want to work with quantum computers, and she was like, you can't do that. But here I am actually working with quantum computers.
Oh yes, you can. And yes, we can. So the questions should not be sci-fi, they should be real.
Yeah,
please.
Thank you. All right, yeah. So I'll talk a little bit about quantum computers and how to apply them to real problems, and which problems will actually be relevant for quantum computers. And before I begin, just a little bit about me. I have a Master of Physics from Aarhus University, which is the second biggest city in Denmark. I also have done a PhD in quantum technology. That's how I know so much about quantum computers. Quantum computers is still kind of a research area, so you need to spend a lot of time getting to know quantum computers before you can actually start working on them. But that will hopefully change within the next 5 to 10 years, where quantum computers will be more useful to everybody. And but as of it now, you have to have at least a PhD in quantum computers in order to even work quantum computers. Then I've spent the last 6 years actually working with software for these quantum computers. So that's what I've been doing, and Yeah, and besides that, I also teach a little bit at Aarhus University in particle physics, something completely different. This is where you just smash particles very, very fast into each other and see what happens. You may have heard about CERN and the LHC in Switzerland. So I know a little bit about that. So if you have any questions about that in the end, please feel free to ask about that as well. All right, so what am I going to talk about? To begin with, I'm going to teach you a little bit about what is quantum mechanics. I'm not going to go full depth on quantum mechanics, just the surface, what is quantum mechanics. I assume most of you have never heard about quantum mechanics or are only vaguely familiar with it, so I need to explain the basis before we actually discuss what is a quantum computer. Then I'll explain to you how does this quantum computer work. Then we'll discuss how do we build a quantum computer, because we cannot build it the same way we build our regular computers, because this is something entirely different. So we need some new platforms to build them. Then when we have built this quantum computer, we also need the software to work on the quantum computer. This is where my work comes in. This is what I do on a regular basis, trying to build software that works on these quantum computers. And finally, I'll discuss which problems will be useful for a quantum computer in the near future. It is not everything that can be calculated on a quantum computer. It's not everything that is suitable to work on a quantum computer. It is only some things. So I'll discuss which things will be suitable on a quantum computer, which will probably be the first things to be calculated on a quantum computer. And of course, there are things that will probably never work on a quantum computer, but then again, I might be wrong. It is very difficult to predict the future. I'm sure if you asked 50 years ago, what will you use a computer for? Many people will say, it won't have that much use. And today, everyone is using a computer for everything. So I might be wrong, and in 50 years, everyone will use quantum computers for everything. All right, so we know that computers are an important part of the everyday work. Every one of us has at least one computer, probably 2 or 3 in our smartphones and smartwatches. So why even bother about quantum computers? Because we know we have these computers, and we know that the computers are just getting faster and faster. This is a plot of something called Moore's law, and Moore's law tells us that the number of transistors in computers is doubling every 2 years, meaning roughly that computers is getting twice as fast every 2 years. All right, then if we want faster computer, we just wait more years to get better computers. And the problem is this cannot keep going on forever, because the computers that we know are getting smaller. 10 years ago, we had these large computers. A laptop was not that common. Now I have a computer in my smartwatch. So computers are getting smaller. But this decrease of the size of computers cannot continue forever. So as of now, transistor sizes is approaching 2 nanometers. And 2 nanometers, that's like 0.0000002 centimeters. So that's very, very small. When things become that small, quantum effects are starting to be taken into account. So this is a board of transistors. This is what is inside computers. This is a rather old board that's inside a computer. And here you see these lines. That's actually wires of electrons and current going through these wires. So obviously, current can't jump between the wires. That's an important part of normal computers. We need to control this current. But when this barrier between the wires becomes very, very small, actually it is possible for the current to jump between the wires. This is something called tunneling, where the electrons that is carrying the charge is jumping through the wall, jumping through the barrier. This is not something that we want to happen in a normal computer, because then the computer breaks down. And when we try to make our computers smaller and smaller, this will start to happen, and it's already starting to happen. So the people making the processors, Intel and AMD, they're starting to experience these problems. So that's a problem for them. And therefore, it's a very good idea to start to think about, can we use this quantum technology or this quantum effects to build faster computer, or should we just give up? So just to explain just how small is the quantum world, consider if we have Here we have the normal scale of things. This is a human, about 1 meter. Mice is a lot smaller, 10 centimeters. When we go smaller, a chicken egg. And then if we go smaller than that, things are starting to become very, very small. We have these eggs, human eggs, plant cells, so this is very small. If some of you have ever looked inside a microscope, this is what you might see. And this is very small bacteria that move around everywhere, something we never see, but is everywhere. And viruses, something that I guess everyone has been familiar with for the last couple of years. But we need to go smaller than that in order to go into the quantum world. We need to go below 10 nanometers. And remember, a nanometer, that's a 0 and then a dot and then 6 zeros. And then you start your number. So it's very, very small. And down in this scale, atoms and proteins and molecules are the things that behave, that works well. And these behave within the quantum realm. They have these weird laws where they behave differently and can do different stuff than we can in this classical world. So back in the days, a long time ago, we thought that atoms, which are these very small things that everything is built of, that these atoms work just like a solar system. In the middle, we have the nucleus, and then around that, these electrons are circling like planets around the sun. Very easy to understand, and probably some of you have seen this picture throughout your education, if you ever had taken a physics course in elementary school or something like that. This is, however, not the way atoms work. In fact, atoms are better described by this quantum mechanical model, where we still have the nucleus in the middle, but the electrons are not actually placed around it. They're more in a kind of cloud around it, and they can be multiple places at one time. So they're allowed to be several places at one time. That would be the same as me being several places at one time. I could be in Denmark and here at the same time. That's very, very weird. But electrons can do that because they're very small and they follow the quantum mechanical rules. And then their position is described by a probability distribution, meaning that depending on that their position is dependent on probability, meaning that there might be a 50% chance that I'm here and a 50% chance that I'm in Denmark. But I'm in both places at the same time. A famous experiment of this is the Schrödinger's cat, where an old quantum physicist tried to explain this principle, the superposition principle, the fact that you can be at two places at once. He explained it using a cat, which he placed in a box, and then in the box he also placed this random poisonous gas that will be released at some random point. And then he closes the box. And when the poisonous gas is released, the cat dies. But he doesn't know when the cat dies, because he doesn't know when the poisonous gas is released. So when the box is closed, the cat is both alive and dead at the same time. That is what is called Schrödinger's cat. You may have heard of this. It's a very brutal way to explaining quantum mechanics, but it's apparently the way physicists prefer to explain it. So we want to use this things in computer. We want to use this quantum principle and this Schrödinger's cat inside quantum computers. So classical computers, and by classical I mean normal computers, the ones that you own and operate, they're all based on these bits. So a bit is basically what is a transistor. So those are the ones that we have millions of, and a bit is either 1 or 0. It cannot be both at the same time. It has to be 1 or 0. And you may have seen these depictions of computers with a lot of ones and zeros, and that's basically what we mean when these pictures are there, that everything is built on ones and zeros. And when you have a million of ones and zeros, there are a lot of combinations, and then every combination means something, and that is shown on the screen on your computer. So that is very nice. That's a quick course on how regular computers work. Today we don't work with these zeros and ones anymore. We work in higher level programming languages like Python or C++ or whatever you use in your normal day-to-day businesses. But when it comes to quantum computers, we're not that far ahead. So we are still working actually with these bits, but we're working with something called a quantum bit. And a quantum bit, also known as a qubit, is something that uses this superposition principle, being able to be both in the 0 state and the 1 state at the same time. So instead, the state of the system is described by this probability distribution, meaning that in this case, there is alpha% chance that it's in the 0th position and beta% chance that it's in the 1 position. And that is, again, very weird, because how can a computer do two things at the same time with only one bit? And that is what we want to use in quantum computers. It is, however, not that simple, because the second we look at the qubit, they decide which state they want to be in. So the second I look at my qubit, it may turn out that it ends up in the 0 state, but it also may be that I could look at another time and then it would be in the 1 state. I don't know that previously. I only know the probability of it being in one or the other state. So that is some of the problems that we're still working on when we develop quantum software. And that is why one of the reasons why the quantum computers are not currently working and currently solving all of your problems. All right. But we can also work on these qubits. Back in the days when we worked with bits instead of Python and C++, but worked directly with the classical bits, what we could do, for example, was change it from a 0 to a 1. And then we could change it back. And to a 1, back. 0, 1, 0, 1. That's all we could do with the classical bits. And here I have a classical gate. If you're very old, have ever tried to work with punch cards, which was what came before Python, then this is actually what you work with. You build these circuits with gates like this, and then you change the bits from 0 to 1 and back again. And that's how you build your programming language. So whenever you build a script, you just changed zeros and ones. Now, of course, we do it much more simple in Python or C++ or Rust or whatever you're using. It's a bit different quantum mechanically. Here, we have different gates, because now we can be everywhere on this sphere, meaning that we can not just be in the 1 and the 0 state, but we can work around the surface of this sphere, meaning that I can do a gate that translates moving around the x-axis of this gate, of this qubit. And I can also make one that moves around the y-axis. Then it would rotate the arrow around. And I can do gates that rotate around the z-axis, and I can rotate other places, meaning that I can combine things in a lot more different ways than what I could if I just had being either 1 or 0. Now I can change into different probabilities, different combinations of 1 and 0. And that's something completely different and very nice. It may not seem very nice to you because you don't know the consequences yet, but hopefully I'll try to elaborate on that. So if you have more than one qubit, we can do other gates, for example, this controlled NOT gate. That basically means that if the first qubit is in the 0th state, nothing happens to the second qubit. But if the first qubit that is up here, first is in 0, second is in 0, then output is still 0. And the first is in the 0, the second is in 1, nothing happens. But if the x qubit up here is in the 1 state, then we change the state of the y qubit, meaning that if we have x equal to 1, y equal to 0, then we get a 1, 1 result out. And in the other case where x is equal to 1 and y is equal to 0, then we get a 1x result out. This is very nice because that means that we are able to entangle qubits. So if I, for example, use this circuit here, where I start both qubits in a 0, 0 state, then I change the first qubit to being both in a 0 and a 1 state at the same time. That is what this Hadamard gate, it's called this H gate, is doing. And then I do this controlled NOT gate. Then I create this superposition of the two qubits, where the two qubits are at the same time both in state 0, 0 and both in state 1, 1. This is very nice, because this means if I measure one of the qubits, say the first qubit, and I measure that to be 0, then I know without looking at the other qubit what state it's in. I know it should also be in the 0 state, because then this is the only available option. If I measure the first qubit in the 1 state, then I know the other qubit must also be in the 1 state. And this is very nice. This means that I can know things without actually looking at them. And that is an extremely nice property that is impossible to find anywhere else in the world. You need to do this quantum stuff in order to be able to know things without actually looking at them. This, of course, we can combine into more qubits using here 4 qubits, where we rotate them around this sphere, and then we can entangle them using these entangling controlled NOT gates, meaning that we can have, instead of just 2 qubits, we can have here a set of 4 qubits, where I would just need to measure one of the qubits, and then I know what the 3 other qubits are doing. Again, very nice, because I just need to look at one qubit and know what every other qubit is doing. Imagine doing a calculation, and you just need to do a part of the calculation, then you know the end result. This is something that's extremely useful in many business cases. All right, so let's discuss how to build such a quantum computer. So there are many ways to build it, and still they're competing on how to build the best quantum computer. We're not done actually figuring out how to build a quantum computer. So one of the ideas is to use something called superconducting circuits. This is something that some of the big companies are trying to do. For example, Google, that you may know, and IBM are trying to build a superconducting circuit quantum computer. Another possibility is photonic circuits, meaning that you use light to make a quantum computer. Here it's a little bit more smaller companies that you may or may not have heard of that are trying to do that. Then something called trapped ion computers, where you use atoms, you know, these small atoms that are quantum mechanical, trap those in a magnetic field, and then use those as quantum computers. And here we have companies like IonQ and Quantinuum, which are owned by Honeywell, that you may know. Then Microsoft is doing something called topological qubits, which is some brand new technology that they're still very much in the beginning of researching on. If it works, it will be very nice, but at the moment it's purely research, so they're not really working yet. Then something called quantum annealing, which is the oldest quantum computing company in the world, called D-Wave. They started in 1999 doing this, so a long time ago. And they actually have these quantum computers, so they look like this. This is actually just a big fridge with the quantum computer inside it. I'll come back to why it's a big fridge. And then something called neutral atom circuits, where they're working on catching atoms using light. So it may be that any one of these technologies will be the way to build a quantum computer in the future. But as of now, it might be any one of those or someone that I haven't even mentioned here. All right. So as I mentioned, many large hardware providers, IBM or Google, or even this Chinese company Alibaba, is working on these superconducting circuits. So superconducting circuits are very nice because they're based on what we have in normal computers. They have these inductors that you may know, capacitors, which is also a completely normal electrical component inside of computers. And then they have added this Josephson junction, which is some weird quantum mechanical component. What it actually is a piece of wire that you cut in the middle. And then, because of this quantum mechanical tunneling effect, electrons are able to jump between this cut. Even though they shouldn't be able to travel through the wire, they can jump. And that's this quantum mechanical effect that makes the quantum computer. The negative thing is this only works at minus 273 degrees. It's very, very cold. That's closest to the absolute coldest that the universe can get. So you need a very, very big cooler in order to go down there. And here we actually have a picture of such a device here. So each of these 4 squares, that's a qubit. So here we have 4 qubits connected to each other, and these weird-looking radiator stuff, that's actually inductors, a normal component from computers. And here you have a computer, or the big cooler. So this small chip is placed inside here, and then all of this thing is built around it in order to control it, and then it's put inside a fridge. That's very cold, minus 273 degrees. All right, so some of the nice time about this is that it's very fast, and it has very good fidelity, meaning that it does what we want it to do, at least 99.5% of the time. That's quite all right. Not as good as a regular computer, which does what we want 100% of the time. It's difficult to connect these qubits, but it's doable to build, and we can do it with off-the-shelf components because these inductors and capacitors are completely normal. So it is a promising way to build quantum computers. All right. Another approach could be these trapped ions, where we catch ions that have a charge. You've maybe tried to consider a statical charge whenever you get a shock. I know Nikola Tesla is from Serbia, I think, and he is one of the founders of figuring out how electrical charge work. And he found out, among other things, that atoms have charge, so you can catch them using a magnetic field. And that is what they do with these trapped ions. Here's a picture of trapped ions, and if we zoom in on that, we can actually see here is the trap where they have trapped the ions in the middle. And if we zoom in again, we can see that here is 7 ions lying on a line, and these are our qubits, which we can actually see. So this is a very, very zoomed in. And the good thing about this is that all the qubits are connected, so they are talking to each other. That's very nice. Again, a problem is that you have to go to minus 273 degrees. And it's also very slow compared to superconducting circuits. But they live a long time, they live forever. They have a low speed, but they work how we want them to work 99.95% of the time. And that's good. We're approaching 100%. Very well connected, but they're kind of difficult to make. So that's a great challenge. All right. Then mentioning the last I'll mention is using, or one of the last is using neutral atoms instead of these charged atoms, and then this time you catch them using laser light. So you shine laser light in from both ends here, and then you create sort of wells where you can catch these atoms, and this is kind of like this tray that may look like you're trying to collect eggs in an egg tray, but these are actually atoms that they have collected in this tray that they have made using laser light. It's very amazing, again, and it's just as fast as superconducting circuits. But again, you have to go to these minus 273 degrees. So that is a problem. Yeah, so again, they live for a long time, very fast, good fidelity, but it's difficult to connect the atoms. It's difficult to scale, and it's very specialized. You need to have these tables of laser light where you have mirrors and lenses where you send through the lights. Not something that you usually like to have in your computer department. All right, so another thing is you can use light as a quantum computer. Light is actually quantum mechanics. The good thing about light is that we have a lot of it, and it's easy to create, and it can be used in room temperature. We can see that because there is a lot of light in here today, at least for me. But the way we do this now is, again, using the light, sending it in as small wave packages, then putting it into tubes where it's swirled around, and the light is changed in its different components, which creates these qubits from the light. Yeah, so this is very long-lived. As we can see, light doesn't disappear when you have turned it on. They live for a long time, and here, seconds is a long time. The speed is, of course, the speed of light. So that's very nice in this technology. It has quite a low fidelity, just around 99%, and it's difficult to connect or to make light interact with anything else than when it disappears. So it may be a useful way to build quantum computers. Finally, I should mention these quantum annealers that are very far ahead in terms of the number of qubits. They have around 5,000 qubits in some of their machines. The others are around 100, so that's a lot more. But unfortunately, these computers work in a bit differently, meaning that they're not universal quantum computers. They're more used to find optimum in optimization problems. And they work simply by having some cost function here, which you can then gradually evolve and then find the lowest point in your cost function and then optimizing your problem. So they're quite neat. I don't think they'll ever revolutionize anything, but they're an old technology, and you have probably heard of them if you have ever heard of quantum computers, because these were the first ones. And it's also very nice that you can actually see how a quantum computer looks. Looks like this. Inside of this, you have this cooler and this gold thing we saw before, and then the chip is in the middle of that. All right. So the number of qubits is also growing. We need, of course, a lot of qubits. I just mentioned that we have millions of normal bits inside regular computers or inside my smartwatch. And we have around 100. IBM has 433 qubits in their biggest quantum computer. But they're expecting that the number of qubits will grow exponentially in the coming years. So this year, they're expected to reveal a quantum computer with more than 1,000 qubits. Hopefully, they're revealing it within the next month, because 2023 is coming to an end. And then next year, or 2025, they hopefully will go up to 4,000 qubits. So it's very nice. The number of qubits is increasing, and we need a lot of qubits in order to actually calculate something. Like we have a lot of bits in our regular computers. Luckily, we don't need just as many bits as we have in normal computers, but I'll come back to that. All right. So not all qubits are created equally. We know the bits inside our computers, our regular computers, our smartwatch, smartphones, they work perfectly. They always do the things we want. That is not the case for quantum bits. So classical bits, they make one error around every 10 years. I mean, I don't think any one of you has a computer that has lived for 10 years. So that's an irrelevant rate of error. It never happens. But actually, majority of these computers are also error corrected, meaning that for every bit there is an amount of bit that does the same thing, and then if one of them makes a mistake, then the other will be like, no, 9 of us says it's this thing that's right, and the other one does the wrong thing. Then you know the majority is probably right. So kind of like a democracy for classical bits or quantum bits. Yeah, and current quantum bits are not perfect, far from perfect. They have many errors each second. So you hopefully see that if you make an error each second, then it's a very bad computer. But if you make an error each 10 years, then it doesn't matter. But in order to get error-free, we need to work on it. We need to figure out how to correct these errors. Yeah, so here's an example of an error. We have 001101, and then suddenly this middle one changes to a 0. That's an error, unless I meant to do it. But we need to fix those problems, because those errors should only happen every 10 years and not every second. Yeah, luckily, when doing errors, it's a possibility to learn, so we're still learning a lot in the quantum computer field. All right, so when will we actually be able to use these quantum computers? So here's a plot of the number of bits here on the vertical axis, starting from 1 bit all the way up to the highest number of bits that IBM have, this 433. When we're below 30 or 40 qubits, then this is something that we can just simulate on a regular classical computer. But when we go beyond 40 qubits, it's something that we cannot simply calculate on a normal computer. So it's something new, and that's very nice. However, on the horizontal axis, I have the rate of error, meaning that if this error rate is too high, then we cannot calculate anything interesting on the current computers. So currently we have a lot of big computers, but they're too noisy. They make too many errors, so we cannot do anything with them. We also have some small computers that are better with less error, but they're not big enough to do anything that a classical computer cannot do. So what we're hoping for is that soon we'll move up into this green triangle, and that is where the computers are big enough, the quantum computers are big enough that we cannot do the same thing on a classical computer, and they're perfect enough. They do a very few errors, so they can actually calculate something that is useful on them. And right now we call this state, where we're not in the green area, we call this the noisy intermediate scale quantum computer, or the NISQ era. And we're currently there and figuring out how do we do this stuff with these noisy, very bad computers. But I guess, or I hope, of what will be needed in order to calculate something very, very nice is that we need around 50 qubits. And they need to be able to connect to each other, all of them, and then they have to have little to no noise. So right now a big problem is the noise, a big problem is that they're not all-to-all connected, and a problem is if you have all-to-all connected qubits with little noise, like Continuum has here, then you have too few qubits. You still need more qubits in order to move up in this green area. But hopefully that will happen anytime soon. Yeah, and we call that a fault-tolerant computer whenever we get that. All right. So what do we do with these qubits? So right now, there are these NISQ algorithms, something called a quantum approximate optimization algorithm and a variational quantum eigensolver algorithm, which can do something. And then there are these fault-tolerant algorithms, the search algorithm and a phase estimation and a factorization algorithm that can be used to solve problems. These NISQ algorithms, there are no promise that they actually work, but we can do them today. So we can work on them and we can try to see what happens. The fault-tolerant algorithms are proven to be better than the classical algorithms, meaning that they are proven to beat normal computers, but they're not working yet. So that's an issue. So currently we're working on these algorithms because we don't have good enough computers to work on these algorithms. All right. So just a quick word about what is this VQE, or this variational quantum eigensolver. And it's primarily used for chemistry calculations at the moment. So that could be calculating molecules or larger molecules like proteins or enzymes. These things could be used, for example, in drug discovery, something which is very nice. And this is basically based on something called the variational principle. And this is some physical principle that you don't need to know the details about. But this means that whatever quantum state I make, I'll never go below the lowest energy of this molecule. So I can always try to make a better guess, and then gradually I get closer to the energy of the molecule. And I want to know the energy of the molecule, because that molecule, if I know the energy of that molecule, I can maybe turn that into a drug that could cure, for example, COVID-19 or the next big pandemic. All right, and this has actually been done, this experiment or this calculation. You build a circuit, a quantum circuit like this, where you have some gates that changes the qubits and then entangle them like these controlled NOT gates. And then you build that circuit here on a superconducting computer where you have 7 qubits. And then you're capable of actually calculating the energy that is these black dots, that is the calculated energy of a quantum computer, of a small molecule, and this is actually the smallest molecule in the world. So a very simple calculation, but they proved that they can do this already back in 2017. So we have come a bit further than this, but this was the first demonstration of a quantum algorithm actually working. which was a huge breakthrough back then. All right. Grover search, on the other hand, is a perfect algorithm. We know it works. And this could be used to search databases. So imagine you have a large database of something and you want to search for the right solution. Then you can use Grover search and you can find the answer faster than you can do on a regular computer. This is very nice because a lot of problems is actually search problems. It's based on something called amplitude amplification. Again, this is something physics, but it's very nice. And it promises you that you can increase speed from finding something in n time to square root of n time. That probably means nothing to most of you, but an example would be if I make my database 100 times bigger, then it would take 100 times as long time to find the right answer on a normal computer. However, on a classical computer, it will only take the square root of 100, meaning 10 times as long time. So that is very nice that we save some time. I mean, waiting 100 hours is a lot worse than waiting 10 hours for something. And it is based on circuits like this, where you start your qubits in this zero state, do some gates, and then you entangle the qubits. And then what you do is you do this diffusion operator right here, which basically rotates your answer into the right answer. So in the beginning, your answer starts here, being close to the wrong answer, but then when you do this rotation, the arrow moves closer to this arrow, which is the right answer. And that is a rough way to explain how this works. Of course, there's a lot of math behind this, but it's nice because it can make search algorithms go a lot faster. All right, so McKinsey expects quantum computing to have an advantage in different fields. They're predicting primarily that life sciences, it will have a big impact there. So that would be biology, drug discovery, chemistry. But it also expects a lot of financial services to be affected by this, especially the optimization and search. That is this Grover algorithm. Also in travel, transport, and logistics. And we see this is basically where McKinsey thinks will have most impact. Life sciences, that is the biggest one. That is where things will happen soonest. Financial services, and then transport and logistics. Whenever this Grover search happens, then a lot of different things will be affected as well. So the first use case I want to talk about is this drug discovery, this life science, where we can find new molecules that can be used as drugs. And that is because that molecules are quantum mechanical. So they work by a quantum mechanical principle, meaning that drugs are quantum mechanical. When you put them into your body, what happens inside of you is quantum mechanical. So therefore, it's a very good idea to use a quantum computer to figure out how that works inside of your body before I just give you some random pill that I found on the floor. Yeah. So pharma companies, they're trying to whenever they make drugs, what they're trying to is figuring out what does this drug do before actually giving it to people. But that costs a lot of money. So what they do is they start with maybe 1 million different candidates for drugs, and then they have to figure out we can't test 1 million drugs. We have to figure out which should we try. So they narrow it down to 250 maybe, and then they try those drugs on animals and see which kills the animals and which could we maybe try to give to humans. And then they end up with maybe 5 compounds that they try on humans. Hopefully no humans will be killed here, and then hopefully one drug will be developed in the end. But this costs a lot of money. Around 20% of the income of pharma companies is spent on development, and they spend roughly, and this is per drug, roughly $2.5 billion and 10 to 12 years every time they develop a new drug. That's a lot of money. And of those 2.5, roughly half and 3 years is spent before even developing the drug and trying it on animals or people. And less than 12% of the drugs that goes to clinical trials that is given to people actually end up being approved. So there is a huge potential in making the pre-clinical trials, the computer trials, better before actually trying out the drugs on humans. So one of the limitations of this computer-assisted drug development is that the result is not very accurate because we're using normal computers like this one to calculate the drugs, and they're not very precise because it's very, very complex, some of these molecules. An example of this is if you're supposed to discover a drug at the size of penicillin, then on a normal computer that would require 1 and then 86 with 86 zeros behind it. That's a lot of zeros, and that's actually more transistors, more bits than there are atoms in the observable universe. So that is way too many that we can build. However, on a quantum computer, if you give me 286 qubits, that works perfectly. I have to say that works perfectly. No error, fully connected. Then I'm able to figure out exactly how a drug at the size of penicillin works. So that's very nice. That's a huge amount of savings on a computer. Another process where the quantum computer could be interesting is in logistics. Delivering and handling goods is a big business, and it's $1 billion business. And finding the optimal path for these flights and ships is very important. And a quantum computer, we can do this faster using this Grover search. Taken as an example, so why is this difficult? If we consider a single ship going around the world with containers, then if we require that ship to visit 10 harbors out of 100 harbors, and then we have to figure out which 10 harbors gives us the most revenue of visiting, then there are more than 10,000 billion possibilities, and just one of them is the best option. That's very, very difficult to calculate and figuring out the best option. However, this isn't even the worst part. Realistically, a big shipping company has around 500 ships and there are 500 harbors. And they have to figure out which harbors should we visit in the right order. But a quantum computer will be much better at figuring this out than a normal computer. The final use case that I want to mention is this financial products, because obviously there are a lot of money in finance. And that's a very common problem. This could be building your portfolio, figuring out which stock should I buy, and then derivative pricing, something a little more exotic than that, but something that banks actually figure out using Monte Carlo simulations on regular computers, but it's very difficult. And again, a quantum computer can search this in parallel and optimize and figure out the results in a faster way. So to take a deep dive into this portfolio management, which is which stocks should we buy to increase revenue? Again, seems like an interesting or easy problem, but I mean, if it was an easy problem, we'd all be millionaires right now. So say we have an amount of stocks that we could buy, and then every day we want to know which should we buy and which should we sell in order to increase the revenue. And that is actually a difficult problem because you only have like 8 hours of the stock market being open, and you have to figure out what to buy and what to sell. And realistically, you want to maybe own 100 stock. If you're a big investment bank, you want to own maybe 100 stocks out of 1,000. And then you get 10 and then 139 zeros of different combinations. Again, an extremely high number of combinations. So there are no real way to figuring this out on a normal computer, but on a quantum computer, it'll be much easier. All right, so I come from a company that's called Quantify, and we actually work with these quantum computers. So what we do is that we develop software for quantum computers because quantum computers are a bit difficult to program and operate because, as mentioned, they work in a bit different way. But we develop software as a service to companies. And we access these quantum computers using Amazon Braket and Azure Quantum, because these quantum computers are already available in these regular cloud services. Yeah, we were funded 1.5 years ago, and we have a lot of experts, most of them PhDs in different stuff like me, quantum computing, algorithm development, and high-performance computing, machine learning. So we are very specialized in a lot of the stuff that is needed to solve these problems, but we do not know, we still need the problem. So we need customers that can give us the problem, and then we'll solve it using high-performance computing or quantum computing. Because high-performance computing is very efficient at solving many problems, but again, it's just a normal computer. But it can be used to perform massive calculations, and we are very good at that. And then this quantum computer will usually be part of this high-performance computing center, and we can use that in our software as well to solve these problems. So we believe actually that in order to find the full potential of quantum computers, we need to work together with normal high-performing computers and quantum computers in order to solve whatever problems that different companies will have. So right now we develop high-performance computing that can solve the problems in the real world, and then we build in a little part for the quantum computers. Whenever the quantum computers is ready, that will take over, and the solution will be even faster. So just to point out where we are in the software stack, so we have a lot of software. Down here we have the quantum computing, GPUs, and classical CPUs. Then there are some tools and managed service used to access those. Then we have the algorithms used on those tools. And then on top of that, we have actually the real problems, the portfolio management, route optimization, and drug discovery. And we as a company, we lie up here. We just want to get the problem, fix the problem, and then use some backend, some hardware that we do not own. Because, as mentioned, we do not know which quantum computer will be the best quantum computer in the future, so we don't care. We want to use all of them. All right. The way we build our software is simply that our customers, they get some Python software development kit, then they contact our software, which then contacts the cloud service, where, for example, we have a lot of classical servers in the cloud, and also these quantum servers in the cloud. And then our software will figure out which hardware do we use the most efficiently in order to solve their problem. So my take-home message for today is that quantum computers are not just a classical computer on steroids. If you think of a classical computer, a normal computer, as a car, we can have a normal car, we can have a fast car. Then a quantum computer is not just a Formula 1 car. It is not just a faster car. A quantum computer is something different. It's a spaceship. It can take us to the moon. It can solve very difficult problems that we'll never solve on normal computers, but it will never replace a normal computers. Think of it as a spaceship. Even though we have spaceships, regular cars is still used today. So don't worry, you won't have to replace your normal computer with a quantum computer in the future. But if you're within some of the areas that I just mentioned today, you should probably be aware that a quantum computer will be important for your software in the future. So it's nice to know. But there are still 5 to 10 years before it becomes relevant in those areas, primarily. All right, that's what I wanted to say. I guess now it's time for questions. We have a few minutes. Thank you. Right, I was told the question would come up here. All right, there is a single question. Can the existence of probability of a qubit state slow down, since it may or may not be a value you need at the moment? Yeah, can it exist? Yes, so the qubit has a rate at which it evolves, so qubits can be slow and they can be fast. But when it is in a probability, it will stay in that probability until it's measured, unless there is a lot of noise in them, which there are at the moment. So in that sense, current qubits that will slow down because the noise slows it down. But when we get these fault-tolerant quantum computers, hopefully it will not slow down the qubit state. All right? I hope this answers the questions. I guess that was the only question we have so far. Unless you have want to add any other questions?
I do have a
You have a
question for you.
Oh.
So I understand you got inspired to work in quantum computing after you watched a lot of sci-fi films.
Yeah.
So should we watch nowadays sci-fi films to understand the technologies of what, 10, 20, 30 years from now?
No, I remember the quantum or the sci-fi film I saw as a kid was completely wrong. In those guys, the quantum computers were all in space and flying around, doing things that we cannot do today. So even what I'm guessing today might be wrong, just as what they guessed normal computers would do many years ago. But this is just an educated guess. But do watch some sci-fi movies. They are very, very funny.
Oh, and we should also read some sci-fi books, right?
And also books, yes.
Okay, good. Thanks.
Yeah.
Thanks a lot, Steve.
I think there are some...
good,
yeah.
good. Oh, so I should come so you get the questions.
Yeah,
Okay,
so
I
there are
stay
some
here.
more questions. So can quantum computers endanger traditional cryptographic methods? And yes, that is a good question I haven't at all mentioned, but quantum computers know this. They can do this factorization algorithm, which can basically break RSA, what we use to encrypt normal computers, and that can break it, meaning that when we get good enough quantum computers, all our encryption will break. However, quantum computers also have its own encryption, quantum encryption scheme inside it, meaning that we just need a new way to encrypt our computers. And this is nothing new from what we had before, because as we're building new computers all the time, we still need to update our encryption all the time. So now we just need to update our encryption with quantum computers as well. So yes, it will endanger, but there's still a solution at hand. Yeah. What are the main noise, the sources of noise and decoherence in quantum systems, and how can they be mitigated or corrected? So the main source is interactions with the environment. If I have a qubit, then there will always be something around it. We try to isolate this as much as possible, but it will always be connected to the surroundings by actually thermal noise or actually heat. Remember that we have to cool it down often to 273 degrees. But if it gets hotter than that, errors will be introduced. So one thing one could do is simply just build better isolated qubits and better ways to do that. Another way to mitigate them is to build software that can figure out what happens when the error is introduced and then correct that error. So that is the two ways to fix it. Either build better hardware or build software that can correct the errors of the qubits. All right? I think there are no more questions.
Steve, thanks bunches. It's been amazing.
Thank
you for helping us understand this much better. Thank you everyone for being here. We are now off for a small break. 3:45, we are starting our last session for today with Norma Acevedo, who came in from Germany. Enjoy Belgrade.
Thank you.
I hope it will treat you nice. Even with all this rain, it's still nice. So see you everyone in half an hour, 3:45 here sharp for our last session. Take care.